This is Doc Nylund bringing you a video on the Lorentz Force. Hendrik Lorentz is the stylish fellow you see in the illustration. He actually helped Albert Einstein with the theory of relativity and won a Nobel Prize for something called the Zeeman effect, which is pretty interesting. In this video, I will begin by introducing the Lorentz force on a moving charge, and then apply the concept to a practice problem. This can be a tricky topic for students, so be sure to pay close attention and let's get started. In physics, the Lorentz force, which is sometimes called the magnetic force, falls under the umbrella of electromagnetism. It is a strange force because it only exists under certain conditions. So let me explain. The Lorentz force only affects charged particles, but they have to be moving across a magnetic field and not in the same direction as the magnetic field. Strange, right? Let's investigate further. Let's imagine that we have a magnetic field represented by a capital B that is pointing into the page. In physics, anything pointing into the page is represented by a circle with an X inside, kind of like the back of an arrow. So all 28 of the little arrows are representing the direction of the magnetic field. Now let's imagine there is a proton moving to the right. Well, since the proton is charged, and it is moving across the magnetic field and not in the same direction as the magnetic field, the proton will experience the Lorentz force. If the proton was also moving into or out of the page, parallel to the field, the charge would not experience the Lorentz force. Now, since force is a vector, this leaves us with two important questions. First, how much does the Lorentz force pull on the proton? And second, in what direction does the Lorentz force pull on the proton? Let's start with the magnitude. According to the Lorentz force formula, the magnitude of the force is directly proportional to the charge of the particle, the speed of the particle, the strength of the magnetic field, and sine of the angle between the particle's direction and the magnetic field's direction. Now, the sine operation can be confusing for students, but remember how I said that the Lorentz force is zero if a charged particle moves parallel to the field? That's what the sine is for. The sine operation ensures that the maximum Lorentz force happens at 90 degrees, aka perpendicular, and that zero Lorentz force will happen at 0 degrees, aka parallel. Now let's look at the direction. You may have noticed from my illustration that there are things happening in all three dimensions. Because of this, we need a method for representing three-dimensional relationships. So I reintroduce to you the right-hand rule. Remember, it is very simple. Your right-hand thumb always points in the direction of motion, which in our case is the proton that is moving to the right. Next, point your fingers in the direction of the field, which in our case is towards the screen, or into the page as we call it in physics. With your thumb pointing to the right and your fingers pointing towards the screen, you should notice that your palm is facing upward. So that is the direction of the Lorentz force on our proton, up. Now keep in mind, if it had been an electron or some other negatively charged particle, the Lorentz force would be pulling down. Always remember that the right-hand rule applies to positive charge, and negative charge does the opposite. So let's look back on the original illustration. If the proton is moving to the right, the Lorentz force will be upward. So what effect is that going to have on the particle? Well, anytime a force is continually applied perpendicular to the motion of an object, that object will turn and actually move in uniform circular motion. So believe it or not, this proton would simply travel along a circular path forever and ever, assuming the conditions stayed constant. Next, let's look at a practice problem. Please pause the video and read the prompt. So as instructed, the magnetic field in my illustration is pointing out of the page and has a magnitude or strength of 0.12 Tesla. At the same time, I've drawn an electron moving to the right with a speed of 2.8 times 10 to the fourth meters per second. Now in this problem, I want to find the magnitude and the direction of the Lorentz force on this electron. So let's start with magnitude. Now according to the Lorentz force formula, the force is equal to the product of charge, speed, field strength, and the sine of the angle between the field and the charge's motion. Remember that the charge of an electron is a familiar constant. You should also notice the 90 inside of the sine operation. This should make sense because if the field is pointing out of the page and the electron is moving to the right, those two directions are perpendicular to each other. Now after some substitution and solving, we find that the Lorentz force on the electron is equal to 5.4 times 10 to the negative 16 newtons. So now that we have the magnitude, let's find the direction. If we look back at the illustration, we can use the right-hand rule to find the direction. Remember, we point our thumb in the direction of the moving charge, which is to the right. We point our fingers in the direction of the field, which is out of the page. We find that our palm is facing downward. However, remember that the right-hand rule applies to positive charge, and that negative charge does the opposite. So since the right-hand rule has our palm facing down, the Lorentz force on our negative electron must be up. Notice that the Lorentz force is pulling the electron perpendicular to its motion, just like we saw with the proton. As a result, our electron will move in uniform circular motion. In conclusion, we have successfully found the magnitude and direction of the Lorentz force on our traveling electron. Thank you for watching my video on the Lorentz force. I hope you find it helpful in your journey through electromagnetism. Please feel free to subscribe to my channel and follow me on social media.